value decomposition of the matrix Q. Now, the matrix U, okay, I'm going to do it here as I did it in the class. Instead of writing R's and C and so on, I'm actually going to draw these boxes. And for the sake of specificity today, we'll talk about the other next sometime soon. Let me assume that Q is actually kind of tall, so it has more rows than columns. Then the singular value decomposition of Q is equal to a matrix U that by necessity of the product has to have the same number of rows as Q, and it is squared by definition. So the matrix U is R by R. The matrix sigma is of the same size as the matrix that we are taking the singular value decomposition of, and therefore it has R rows and C columns. Now that matrix is by definition quote-unquote diagonal, and what we mean by diagonal in a rectangular tall matrix is that it is like this, and that part is C by C, right? This part down here being 0. And then we have the VT matrix, which is actually the reason why I write this VT here like this is because the matrix that is on the right side in this product, MATLAB outputs it rotated or transposed, right? So when you do a singular value decomposition on MATLAB and you get these three matrices, you actually don't get the matrix on the right side. You get the transpose of the matrix on the right side, okay? So I just put this little t here to remember. Now the final matrix is equal to a matrix which is C by C. So this is the singular value decomposition of a tall matrix. I've shown it here with 4 dots. These guys here are what we call the singular values, okay? And sigma 1 is bigger than sigma 2, is bigger than sigma 3, etc. And they are always positive. So the singular values are always real and positive and are ordered from large to small. As I say, no matter what the matrix Q is, the singular value decomposition exists. Now, in addition to this thing here, we can say that the matrix U, okay, is, well, it could be complex depending on what the matrix Q was, but for real matrices it's real, and the matrix U is orthonormal. So we can say that U times U transpose is the identity, and it also is true that this matrix is such that V times V transpose is also the identity, and therefore both U and V are orthonormal, okay, or unitary in the case of complexity. Now the singular value decomposition is going to be at the center of our work in many applications, in many things. The rank of a matrix is the number of non-zero singular values. So this is a way to define rank. When we do the singular value decomposition, we just see how many singular values are non-zero. So in a matrix that was 4 by 4, of course, we cannot have a rank of more than 4. If all 4 singular values are non-zero, we say the rank of the matrix is 4. Now, I guess time is such that perhaps what I'll do is tomorrow, when we do the lecture, it's more convenient than to try to move the camera now, which will be a mess, to illustrate some of the numerical examples quickly so that I'll repeat a little bit of what I did yesterday. But just for your own, to be complete, I did mention, or I did talk about the fact that the singular value decomposition has one, well, has a lot of uses, but it has one use that it is worth mentioning right away. Imagine, and I'll illustrate it symbolically like this. Imagine that we have a matrix that is, I don't know, 5 by 3. Okay? And so what we'll get is a 5 by 5, right? Multiplied by a 5 by 3. Multiplied by a 3 by 3, right? Now, let's say that this singular value was 7, this was 2.3, and let's say that this was 0.01. This, of course, is 0, and this is full of numbers. And this is the matrix Q. Then the question is, what is the rank of the matrix Q? Well, the rank of the matrix Q is 3, because there are 3 non-zero singular values. However, we also observe, right, that one of the singular values is significantly smaller than the others. Well, significantly is quite a bit small compared to any of the others. Therefore, we can see that if this 0.01, that this matrix is rank 3, but it kind of wants to be rank 2, right? Because if we just happen to have a 0 here, it would be rank 2. So a question that sometimes comes up is this. The matrix that you have here comes from data. And the fact that it has this very small singular value is not because the real problem has that singular value, but because there's noise. And the noise is distorting the answers, and so you see this thing. Now, in the process of cleaning the matrix, we may be interested to say, well, okay, this Q is 3, but I want to answer the following question. What is the closest matrix to Q that is rank 2? Okay, this one is rank 3. But I want to say, what is the matrix Q bar rank 2 that is, in quotes, closest to Q? Okay, what is the matrix Q bar which is rank 2 that is closest to Q? Well, one way that I do that right away is to say that Q bar is the same left side singular vectors. Oh, by the way, I didn't mention that. The U is called the left side singular vectors. And this is called, obviously, the right side singular vectors. So what I can do is leave the left side singular vectors the same, leave the right side singular vectors the same, and just simply replace the small singular value by a 0, right? And then just do the multiplication. And suddenly, or not suddenly, but easily, I have generated a matrix that is now exactly rank 2, which is very, very close to my original matrix Q that was rank 3. And that matrix may, in some instances, be a pretty good approximation of what the information is after the noise is removed, if we were able to do so. Okay? So, as I said, this material that I made an attempt to repeat for you here is 95% the same as what I did yesterday in the class. The only distinction being, apart from answering a couple of questions, that I actually showed a specific numerical things and we played around with this thing on the board a little bit. But I will in order to make sure that we all got exactly that, you got exactly the same thing, I will tomorrow begin by playing around with a few of the numerical examples, and then we'll all get on the same boat and move forward. So I hope you find this kind of useful enough to make up for our mishap yesterday. All right, thank you.